In this video, I'm going to talk about polarity of molecules worksheet. So there is a notes on the polarity of the molecules, the notes before that basically talk about if you have delta En between 0.5 to 1.7, you put the dipole. And if the delta En is between 0 to 0.49, will be nonpolar, and you draw no dipole. And also it mentioned about whether the dipoles will be present but cancel, or they're not present, or they will form a net dipole moment, or they will not be cancelled at all. So I'm going to use this video to jump directly into like what's the inference if the dipoles are cancelled. How do you know they're cancelled? How do you know they're not cancelled? How do they add up, or how they're not present? So I'm going to do question A, B, C, D, K. A, B, C, D, K. So you first have to find the En number for each element and you label on them. Okay, you use the green chart. And then next is you need to do the math in your mind, is find the delta En between the bonds. Now here, for example, I will only find the bond between C and F because there's a bond here. Never find the bond between F and F because there's no bond between F and F. You see that I only have the bond between C and F, C and F. So F and F, there's no bond, don't find the delta En. So well, in your mind, like delta En between C and F, like 4 minus 2.5 or 2.5 minus 4, and then take absolute value is 1.5. 1.5 is in between the category 0.5 to 1.7, so that we have to draw the dipole from small to big. Okay, from the dipole from small to big. So small is C, big is F. So we're going to draw the dipole from C to F. This is 1.5. You keep that in mind, this is 1.5. This 2 is also the difference is 1.5. So that means they have the same thickness of the dipole. We draw the same thickness of the dipole. Okay, so we like this. And then 1 here. And also 1 on the top from C to carbon. So totally, you want to tell me how many and kind of the bond. I do have 4 polar bond because the delta En is between 0.5 to 1.7 and we draw dipole. So we have 4 polar bond. Okay, now if you look up the muscle sheet that I gave you, these 4 dipoles, they are in tetrahedron, so they are symmetrical because each angle is also 109.5 degrees, so then they are symmetrical if you talk about all 4 dipoles. So these dipoles are in symmetrical. So let me go back here. Symmetrical here, I'm talking about are the dipoles are symmetrical or not. Are the dipoles are symmetrical or not? Okay, so because they are in tetrahedron, each angle is 109.5, that means all the dipoles are in symmetrical. So they are in symmetrical. Now, if they're symmetrical, I do have the dipoles. Yes, the dipoles are present. But because symmetrical, they will be cancel each other. Because symmetrical, they will be cancel each other. So present, but cancel. Okay, they are symmetrical shape because the tetrahedron, and each one I have them. Okay, so they're present but they cancel. If they cancel, that means you assume, oh, when they cancel, that means these dipoles are not present. You can erase them. You can imagine you can erase the dipoles. So then if I have no more dipoles, that means my molecule will be nonpolar because I don't have a winner. No dipoles, the dipoles are cancelled. That means no dipole. No dipole, no winner, nonpolar. Okay. Next question. C and H, there's no dipole because the delta En is only 0.4. But the C and Cl, the difference is 0.5. So we draw the dipole from C to Cl because from small to big. We're going to do the same thing for the other 2 Cl. And they should be the same strength because the difference is 0.5. So then right now you have 4 bonds, but 3 of them are polar and 1 of them are nonpolar. So 3 polar and 1 nonpolar. 3 polar and 1 nonpolar. Okay, you have 4 bonds. So if you have nonpolar, then forget about the nonpolar. Just look up the 3 the polar bonds. So the 3 polar bonds looks like a chicken feet shape go to the bottom. Chicken feet shape go to the bottom. But I have no chicken feet go to the top to be symmetrical. Again, I have 3 bonds, polar bonds go to the bottom. They're like chicken feet shape, go to the bottom. And I have no chicken feet shape go to the top to be symmetrical. So in other words, my shape is not symmetrical. Okay, now I do have dipole. I draw the dipole. The dipoles are present. Because the shape is not symmetrical, that means like for here, like I have all my dipole go to the bottom and nothing on the top. So they cannot be cancelled. And not cancel. So present and not cancel. If they're not cancelled, that means these dipoles are here. Then they will be a polar. That molecule will be a polar molecule because I do have a winner. The dipoles are there. Letter C, CH, CH, they're all 0.4 delta EN. So I don't need to draw any dipole because 0.4 is non-polar covalent. So that means I'm not going to draw anything. So that means I will have 4 non-polar bonds. If I have 4 non-polar bonds, like, well, I'm asking you, hey, are the dipoles symmetrical? Well, since I don't have dipoles, then no question about symmetrical. So I have no dipoles here. Just write no dipoles. Then don't need to worry about symmetrical. Now, because of no dipoles, then you can say the dipoles are not present. I don't have them. If they're not present, that means the molecule will be non-polar. No winner. Okay. Letter D. 2.123 is 0.9. Draw the dipole from H to N. And they have the same strength, so same thickness. Okay, so here I have 3 polar bonds. Okay, now you notice 111, this chicken feet is actually going this direction, go up this direction, go up this direction. So you notice that they all join into the top. So as a result, I have to draw a huge so-called dipole moment, a net dipole moment. It's a thick, thick, thick one. Okay, because this go up, this go up, this go up. Eventually, they will join in somewhere. So this is called net dipole moment, like a net one. It's like, I would not say combine because it's like vector, but it's like net dipole moment. Eventually go up. So this red things go up. So if this eventually go up, I have nothing on the bottom to cancel. Okay, every dipole go up. I have no dipole on the bottom to cancel this red thing. That means my shape for the dipole is not symmetrical. Okay, not symmetrical. Now the dipole, I'm going to say the dipoles are present and form net dipole moment. The dipoles are present and form net dipole moment. The dipoles are present and form net dipole moment. Okay, these 3 join together. So I don't have anything on the bottom to cancel. Alright, so that's the result. The molecule is polar. The molecule is polar because I don't have anything on the bottom to cancel. Now I'm going to do the question K. Okay. Now C2O dipole from C to O. Okay. This is the difference is 1.0. Now the C and F, the difference is 1.5. This also the difference 1.5. So thicker is a bigger delta EN and than the C2O. So I'm going to draw a thicker dipole from C to F. It's a thicker one. It's a bigger one. To represent the delta EN is bigger. So I'm going to draw a thicker one. So these 2, I'm going to use a green pen, and this one, I'm actually using a black pen. Okay, this is a black pen. This is a black pen. So this is a black pen. This is a black pen. And then these 2 are green. They are thicker. Now, please don't, it looks like not too good. This one is not, sorry. You don't want to draw this too thick, okay? This is just black, okay? Don't draw too thick. This black should not be that thick. So maybe I should draw the green one much thicker, so you can tell this is much thicker than that, okay? This should be like a thin color. This should be a thin one. So this should be a thin one. This should be a thin one, okay? Thin. Thinner, okay? This should be a thinner one. Okay, this should be a thinner one. And the green one should be a lot more thicker because the delta EN is more. Okay, so this is a green, thicker. This is a black, thinner. So sorry about this part. It should not be that thick. Okay, it should be thinner one. Okay, now I can tell I have two different kind of the polar bond. I have one polar bond which is black. Okay, the thinner one. I also have another kind of polar bond which is thicker one, but I have two of them. So I'm going to put them separately that to represent they are not the same delta EN. This is the thinner black one. These two are the thicker green ones. Okay, so again, please do not draw this so thick. It should be one line only. Okay, now you can tell, right? The dipoles symmetrical. Now, originally the dipoles are symmetrical if they are the same string. But this, the black one and the green one, they are not the same. The black one is a lot more smaller than the bottom two. So they symmetrical. The dipoles are not symmetrical. So the dipoles, I forgot to write dipoles are. Okay, so dipoles are not symmetrical because the size for the green are not the same as the black. So the dipoles are not symmetrical. They're not symmetrical. So the dipoles are present and not cancel. The dipoles are present but not cancel because this thing has a different strength than the other two. So in this case, my molecule is polar.